Yeah, welcome to one more session on Mathematics 2. This is Sayyid Biban Basha of VVIT, Nambur. And so far we covered the basics of matrices, and in that one, rank, the basic definition, how to compute the rank in especially echelon form and normal form, and its little extension of the normal form is extracting two non-singular matrices from the given matrix by reducing the given matrix into normal form. And also we computed inverse by using Gauss-Jordan method. So these are the topics we covered so far. Now in this session we are going to cover what exactly a linear system, how to compute that. These are all the aspects we cover in that. So please kindly follow. Generally a linear system is nothing but system means simply a group of something, and a linear means here degree 1. So here, a linear system means a group of equations whose degree is at most 1. So let me write down those sample equations here. A11x1, A12x2 plus A13x3 and so on plus A1n xn equal to B1, A21x1, A22x2, A23x3 and so on plus A2n xn equal to B2, A31x1, A32x2, A33x3 and so on plus AN 3n xn equals to B3 and so on. AN1 x1 plus AN2 x2, AN3 x3 and so on plus ANN xn equals to Bn. So this is a standard form of the linear system. This one I'm going to extract and representing that as here Ax equals to B. This one I'm going to express as Ax equals to B, where A is the coefficient matrix. Where A is the coefficient matrix, that means which we are collecting only coefficients of the variables here. So A11, A12, A13 and so on, A1n, A21, A22, A23 and so on, A2n, A31, A32, A33 and so on, A3n and so on, AN1, AN2, AN3 and so on, ANN. This is the a matrix which we collected only the coefficients or the variables. Here the variable is x1 and whose degree 1, x2 whose degree 1, x3 whose degree 1 and so on xn, all the degrees are 1 here. Now x is a variable matrix or unknown matrix. Variable matrix or unknown matrix. Which is x1, x2, x3 and so on xn. This is clearly a what column matrix or a vector. The reason is here the order of A is n by n, and here the variable is either 1 by n or n by 1 if you write. Suppose if I write 1 by n, the matrix multiplication does not exist. That's the reason I wrote n by 1. N by 1. So it gets cancelled, n gets cancelled. Finally, I may get n by 1. So even I suppose to write the constant matrix as also a column matrix as n by 1 means which holds n rows and only one column. Now B is constant matrix which is B1, B2, B3 and so on Bn. So like this I may express the given linear system as this. Now actually what we have to compute is here unknown matrix I need to compute here means in Ax is equals to B, what I expected here in Ax equals to B, I need to figure out what is the x value means I need to compute the what is the unknown matrix. So for that one by we know that cancellation loss. So based on the cancellation loss I may pre-multiply with A inverse on both sides. Then A inverse into B we may get. Then by using associative property I may write here A inverse times A times X equals to A inverse times B. But A inverse times A means I times X equals to A inverse times B. And further I times X means since it is a matrix so I can write X directly A inverse times B. This actual standard method. But here is the difficulty, if the number of variables up to 3 it is quite easy. We can, but if the number of variables are more than 3 or the order of the A is more than 3 by 3, then it might be the computational complexity will be high. So that's the reason this is advised only up to 3 by 3. For 4 by 4 and more we need to follow a different method. So for that reason I'm going to solve this one by using two different procedures. One is called a direct methods. I may try this one using the direct methods. Sorry, direct method. Next one by using a rank method. A simply comparison of the ranks. So here in the direct methods, what I need to do is the possible methods, Cramer's rule, this another name of this one is determinants method, Cramer's rule, matrix inversion method, LU decomposition, Gauss-Jordan's method, or Gauss-Jordan's method, Gauss elimination method. But here by using the direct methods, at most we can able to compute only unique solution if exist. This output will be by using the direct methods. By using direct methods, we may get only unique solution, that too if possible. Means it doesn't give any guarantee that solution exists always to the given given system or given linear system. So what I am trying to do is, to overcome this one, I am moving to next method, which is known as okay, before that, in this one we have, as per the syllabus we have only Gauss elimination method. In addition to that, we may discuss even Gauss-Jordan's method. Only these two we may discuss here. So means this was already covered at lower classes. This is already covered at lower classes. This is also covered at lower classes. But earlier syllabus, according to earlier syllabus, it was there. So we are not going to discuss this one, this one, this one now. Only Gauss-Jordan's method and Gauss elimination method only I am going to discuss in this aspect now. Now the major drawback of this one is, at most we can able to compute a unique solution, but not infinitely many solutions. And to overcome that one, I am moving to the rank based. If I check with the rank based methods, in this what I am trying to do is, here, first I need to figure out what exactly A means, that is coefficient matrix, what exactly B, that is constant matrix. Then I am writing augmented matrix. I need to write augmented matrix, which is, I need to dump the A, and the last column I'm going to add B. Add means only appending. So this is known as augmented matrix. Now what I'm trying here in this is, I'm comparing ranks of A, and if I define augmented matrix as a C, rank of A and rank of C, that is, I am computing what is the rank of C and what is the rank of A. Here the possibilities are like this. The possibilities are like that. Rank comparison. There might be rank of A equals to rank of augmented matrix. Rank of A is not equal to rank of C. So if rank of A equal to rank of C, then the system is said to be consistent, which means solution exists. Consistence means solution exists. Here rank of A is not equal to rank of C means inconsistent. Solution does not exist. If solution does not exist, extension is not possible. So now if solution exists, what I'm trying to do is, what are the possible solutions I'm trying to compute here. If solution exists, the possibilities are unique solution. For that one, rank of A equals to rank of C equals to number of unknowns in X. Then the system will have unique solution. Then if rank of A equal to rank of C is not equal to number of unknowns, obviously will be less than number of unknowns, then the system will have infinitely many solutions. and infinitely many solutions in that one. One of the solution is 0 0 0. Let me rewrite this. In this, x is 0 0 0 and so on, 0 transpose. I want to save my space, that's the reason I wrote as a row wise, and then I use the transpose, means it is a column vector. So this, so whenever one of the, by default this would be the solution in the case of the given system is homogeneous. So this if all the entries are 0, means which is known as the trivial solution. Trivial solution. Now here one more thing we supposed to check, that is in Ax is equal to b, in Ax means the linear system is denoted by this. If Ax is equal to b, in that, if in Ax equals to b, in if capital B is not equal to 0, then the system is said to be non-homogeneous. Homogeneous. If it is a non-homogeneous, what is the thing is it may or may not consistent, may or may not consistent, means solution may exist or solution may not exist. That's the meaning of that. Now if b equal to 0, then the system is said to be homogeneous, which is consistent always, which is consistent always. So for a homogeneous system, solution is always exist. By default 0 0 0 is a solution, which is known as a trivial solution, and infinitely many solutions are also possible. How to compute that, we'll see in this. Now let me recapitulate this again. In this, in today's topic, I'm going to discuss about a linear system. What exactly the linear system is? The linear means the degree is 1, system is a group. So here I'm writing the group of equations. Actually linear system of equations we supposed to write. In this the linear system is a11 x1 plus a12 x2 plus a13 x3 and so on, a1n xn equals to b1. And similarly I wrote the set of n equations. Later as the set of n equations I am trying to express as ax equals to b. In this, a is known as coefficient matrix, means we collected only the coefficients, so that's the reason coefficient matrix. X is unknown matrix, means our variable matrix, which we supposed to compute here. B is a constant matrix, B is a constant matrix, so we collected. In this, X and B are column matrices only, single column is there in that. Now generally to find x value, we supposed to proceed like this. Ax is equal to b, from that I want only x, means here extra a is extra for me, so to eliminate that one I need to multiply, pre-multiply with a inverse on both sides, then I make it finally x is equal to a inverse into b. This is the one of the ancient method to compute the solution of a linear system. But here the drawback of this one is if the order of the matrix is more than 3 by 3, then computing the determinant as well as the cofactor matrix are a tough task. I can't say that they are difficult, I can't say that impossible, it is a tough task. So to avoid that one, we can try the, we can try this to find the solution in another way. So in the way of computing the solutions, hardly I can classify two methods. One is the direct method, next one is a rank based methods. In direct methods we studied at lower classes, Cramer's rule, matrix inversion method, the both you have studied. Even Gauss Jordan method also studied, if I'm not wrong. Now, in addition to that, LE decomposition, Gauss elimination, we are going to discuss here. Here, in the Gauss-Jordan method means to find the inverse of a given matrix, Gauss-Jordan method. What was the output here? The output is a multiplicative identity. So similarly here, in the Gauss elimination method, the output will be an upper triangular matrix. Now, the major drawback of this one is, if the solution exists, the two only unique solution I may find at a time. I may not compute more than that. But to extract all possible solutions, I need to use rank based methods. In this one, we are extracting a coefficient matrix and constant matrix from the given linear system, and I generated augmented matrix. Augmented matrix means already the coefficient matrix is there. The last column is B will be appended to that. That is here for my convenience. I consider it as with the name C. So now what I am trying to do is I am comparing the ranks of A and ranks of C. Fortunately, rank of A calculated means rank of C calculated means rank of A also inbuilt in that one. So no need to find separately two times. Only one time is sufficient for us. Then rank comparison. So if both ranks are same, then system is consistent and solution exists. If rank of A is not equal to rank of C, then the system is inconsistent. The solution does not exist. Here is a bigger question. If solution exists, how many types of solutions are possible here? If solution exists, rank of A equal to rank of C equal to number of unknowns in X, then we find a unique solution. Now in this, rank of A equal to rank of C but not equal to number of unknowns. That means infinitely many solutions. In this case, X is equal to 0, 0, 0, 0. Out of this infinitely many solutions, one of the solution is this 0, 0, 0, 0 and so on transpose. Then which is known as a trivial solution. Now, if you learn a little more about the given linear system, Ax is equal to B, in that one, if B equal to 0, then the B is not equal to 0, then it is set to homogeneous solution. In a for a homogeneous non-homogeneous solution. For a non-homogeneous solution, solution may or may not exist. If B equal to 0, the system is said to be homogeneous, which is consistent always. So far we discussed this one, and how to check this one in the problems we may discuss in next session. Thank you.